Hello, welcome to numerical ship and offshore hydrodynamics. Today is the lecture 59. Today we continue the discussion that we have done in last class, that how we can incorporate the green water load. After that, actually we are going to discuss something on the slamming load. Now, the green water load we apply for a rigid structure. Okay. However, this slamming and green water load again we apply for both flexible structure in the next. Okay. And then we are going to discuss that something on the 3 step bound element FEM-CFD based method. Now, in this full course that we do not touch CFD because it is a several aspect and is out of the scope of this course. However, I would like to introduce some part of it, so that you can have an exposure that frankly speaking, if you really want to have a deep study on this, you have to have some CFD based approach. Okay. I mean the Navier-Stokes based approach to do that anyway, or maybe some particle based approach called smooth particle hydrodynamics. So, those things is required. But however, suppose why I put it here, the simple reason is that if you have that particular solver, the NS solver or the SPH based solver, how beautifully you can use it here, that again we are going to discuss. So, this is the idea of having some discussion on that part also. Okay. So, and this is the keyword that you have to use to get this lecture. Now, let us start that how we can incorporate the green water load using the IRA based method. Now, in the previous class we actually find out that how we can get the P total, or we can call the P tot. It is the pressure. However, we need a green water load, or we call this as green water. So, just FGW. So, we need actually the green water load, not the pressure. Now, here you can see, like if I have, let me draw again this picture. We say that we are having the pressure at this particular point. Now, as I said, there are various way actually I can convert this pressure to the load or the force. Now, here you have this pressure, and then what you can do is that you can do some cross sections along this, along the length. Now, normally if the length between perpendicular or LBP is the length between perpendicular. So, we can actually try to figure out what is the green water load till LBP by 3. So, that may be the good estimation of this. Now, what we can do is till LBP by 3 I can take lot of stations, okay, and then each station actually I can get the green water pressure. Now, so therefore, what you can get. So, now this is my stations from the forward perpendicular. So, this is my forward perpendicular, and this is actually if I calculate from here, this may be the 2 into 2/3 of LBP, let us call. Okay. So, from this point actually you are trying to calculate the green water pressure, all the points. So, maybe you can have this is the load, it should be less, this the load, this is the load, maybe this is the load, this is the load, this is the load, let us say this is the load. So, I can get a curve like this, or you can call the pressure curve. Now, if you integrate the entire thing and if you multiply by NZ, then definitely you can get the green water load. So, this is one way of getting it. So, green water T. So, it is nothing but integration of 2/3 LBP to to the total length LBP, and then you integrate this pressure, that the green water pressure P tot multiply by the NZ into dx. So, this is how we can get the total pressure. Okay. So, so this is one way, and then okay, I miss one thing here. Now, can you guess that what I miss over here? Like, see, suppose this is my station. Now, if you take this take a body plan view. So, actually I am talking about this station, right. Now, here again I am, so this if I take it in this plane, it should be look like this. Now, here I only find out the pressure at the this point. So, I should to, in order to get the full thing, I must get the integrate along, I mean it should be a surface integral, not a line integral, right. So, therefore, this must be multiplied by the beam of that particular section. Now, it is complete, right. So, now I have this the green water F G W is nothing but integration from 2/3 LBP to LBP, and then I integrate this P dot T, of course, it is T, and then it is equals to B into X. Now, I would like to say it is N Z into dx. So, that should be the force. Now, once you have the force, if you multiply with the now the moment. So, m green water, this T should be the multiply with the moment term. So, this is the two equation that actually I can get the green water load. Now, this approach is fair enough, one can take it, but suppose if your idea to just give some approximation using some approximation here also. So, sometimes what normally as a homework what you can take is as follows, like what you could do is, now if I see the ship from the top. So, let us say this is the ship, and suppose you are getting at this particular point you are getting the pressure. So, what you could do is as follows, you have to understand that sometimes maybe you the best idea is to you get everywhere, you get, as I said, you get the pressure at each point. So, then what you are doing, so you need this pressure, and now this length is nothing but your L by 3. So, you integrate this, in fact, this and this both are same, and then again you can find out the pressure. So, that is what I said, the pressure and multiply by this thing, which is so it is P tot T into B x into N z into dx. So, this is one thing. Now, the other part what you could do as follows, you take a middle point somewhere here, a single point, okay, and then you can get the area. Now, this is, let us say this is the area of this particular thing, and this is any arbitrary point. Okay. So, what you can do it as a homework, you take this point and you calculate the a single point, you calculate what is the total pressure at this particular point, and then you multiply with this entire area that actually you want to do, and then you multiply it by the NZ. So, this is another way you could do that. Now, third way that third alternative way, you can again do the same thing as follows. I am drawing again the same thing here. So, I pick this point. Okay, now I am drawing the profile view like this. So, now this is the L by 3, I am picking the middle point of the L by 3 and I can approximate a function which actually behave like a polynomial or kind of a impulse function kind of thing, because so we can approximate a function. So, you can call it a hat function. Now, it is not actually hat, it is not linear. So, it is it is up to you, you can fit a cubic polynomial or even you can try with Gaussian also. That is what the idea of the smooth particle hydrodynamics itself. So, from that also you can get this idea, like you can fit a polynomial curve. So, here that value is 0, here this value is 0 and here that value is equals to p dot. Okay. And then you fit a cubic curve, and then when you calculate the green water load, so at that point you can use that F, the green water load is nothing but that now you are integrating this again this function. So, it is a polynomial function f x, right, and then it is 0 to L and then it is B x into n z into d x, that is also possible. Now, why this f x is f x? Now, here you can say that f of 0 equal to 0. Now, f of L by 3 that is equal to 0 and then f at x p equal to pressure total. That is the nature of the curve. Okay. And then you can approximate some kind of this function f x, and again you can do this green water loading. So, that is how you can approximate the green water load. So, this is one. Now, how you can incorporate into the IRF based solution. Now, if you know that what is the IRF based solution, it is M. I am just writing a single degrees of freedom heap, because you can extend, because you know this very well. So, it is x double dot plus it is 0 to infinity b tau x dot t minus tau plus c into x t. Now, and this right hand side actually you can write my f of exciting force, right. Now, with this actually you can add this f of green water. Okay. So, now this is how actually one can incorporate the green water loading into the IRF based solution. Okay. Now, you know that how to write the algorithm very well, right. So, here you will get the value for the heap. So, from here you could get the value for let us say x 3 t. Now, if you use now here you so here x 5 equal to 0. So, you cannot get the full benefit of it, of course. In order to get that, you have to incorporate the coupled equation also, right. So, I am just writing it. If you suppose if I want to solve heap and pitch coupling, then how we could do that? Okay, let me write it and then we can move to the next topic. Okay, I am just quickly write it. So, it should be m plus a 3 3 infinity into x double dot 3 t and then plus 0 to infinity it is b 3 3 tau into x dot 3 into t minus tau plus c 3 3 into x 3 t, and then we have to add the cross coupling term, which is a 3 5 infinity into x double dot 5 t plus 0 to infinity into b 3 5 tau into x dot 5 into t minus tau d tau, okay, I miss the d tau over here, okay, plus C 3 5 into x 5 t, and that should be equal to f of exciting plus f of green water. And then similarly, we have to write for the pitch I plus f 5 5 infinity into x double dot 5 into t plus 0 to infinity b 5 5 tau into x dot 5 t minus tau, and then so on, this equal to that f 3. So, it is f 5 exciting plus movement of green water. Now, this is how actually you can use this green water, and then you can find the value, right. And one thing actually I forgot numerically, how we can get the, now I know how you get the z relative. Z relative, I know that, you know that this is t equal to it is coming here x 3 t minus x p into x 5 t, right. So, then actually V relative t also similar way you can get, it is V 3 t minus x p into V 5 t, right. Now, you have problem with the derivative of the V relative, because you have to find out del del t of V relative, that also you need to find, right. How get the derivative of the V relative, then you know that is actually you can use the forward difference scheme. So, you can take V relative t minus V relative t minus delta t divided by delta t. Okay. So, now I think you are ready to incorporate this green water into the solution of your IRF based system. So, try to do that. I think by this time you have already the code for the IRF based solution. So, now we just incorporate this term into the IRF based solution. Now, let me now just move into the next part, that the slamming. Now, here what I am going to do is that I am just giving you the key aspect of it, okay. And then and I just see, suppose you have this hydrodynamic code, the semi analytic code, how you can incorporate the green water and the slamming. Now, this is the whole setup. Now, here the F total, again you know this combination of this exciting force plus radiation force, and then you need to add again in the right hand side these two term, right. Now, how you can write it using the semi analytic method, okay, or the modal super. Before that actually it is the Wagner theory, it is very well known theory. You can refer this classical Wagner, and also at the end I put the reference from that book also, you can get that the final expression of the slamming load. Now, but just to give you a brief, that suppose this is the half breadth of the, so it is a like if this is the ship, not the ship, now here is the body plan. Now this one is this line. Now, this actually penetrate into the water, and because of that some water is piled up, right. Now, this part is basically the free surface. Now, this is the distance from this half, you can say that the middle plane, okay. So, that y z plane passing through y equal to 0. So, x z plane passing through y equal to 0. So, this is this one is that line, okay. Actually the body plan, and this is the line, okay, the symmetric line. So, now I just taking the half part of it, right. So, this distance is the c, and now if I take this angle as beta, because it is a slope, you can take the slope also, because mostly the ship is not like this. So, maybe if this is the line of the ship, so you can take the slope also. and this is the angle beta, and now this point is actually it is z equal to 0. So, h t is the how it penetrate into the water, from there to the z equal to 0 is h t. Okay. And now this is the setup. Now, if you find out that what is the value of h t and what is the value of the beta, and then this is the point actually till this point actually shift. So, this is the free surface. So, you know this point. So, you know this distance also. Once you know this data, then you can directly use that slamming pressure with respect to this formula. Now, here you can see here that beta you know the relative velocity, of course, we discuss a lot about the relative velocity. You know what is the c, that is the distance between the y equal to 0 to the free surface, that y distance. Okay. So, then you know what is the slamming pressure, and this is how actually incorporate the green water pressure. So, these two this we discussed a lot. This we are simply using this the Wagner formula. Now, idea is how I can incorporate. So, in the solution. Now, if you look at this solution, here I am integrating, actually it is from, because it is we have to do that from 0 to L. Now, here the idea is how I can incorporate the green water load and the slamming load into this particular solution, right. Now, here this is the little bit tricky part, I would say. It is not complex, of course, but how I write this the green water and how I can write the slamming. Now, the idea is when you calculate the green water and slamming, you can take a rigid body mode, okay, and then you can get the pressure assuming that it is a rigid body mode, and then you can multiply with the mode shape to get the slamming load as well as the green water load. So, this is the idea. So, now that again that in fact is not the slamming, even for the green water load also it is the same. So, you assume a rigid body. So, you assume a rigid body and then you calculate what is the P green water, the pressure, total pressure, and also you can calculate using the Wagner method what is the now slam. So, I just write P s, that slamming pressure at the point at any time t. Now, there is a many way to replicate this. The popular idea, as I said, that you can assume this as a impact load, which is normally, if you look at this journal paper everywhere, it is we can call the both are kind of impact. So, then impact load is the best way to define this, that load, that F and whatever the green water or it is slamming does not matter, you can just write that is a P, let me write P t, because it could be P slamming, it could be pressure due to the green water, and then you can multiply with the Dirac delta function x minus x naught. You can do that. This is one way of doing it, right. In fact, this is the best way of doing it, assuming that it is a this is a impact load impacting on that particular thing, and then when you integrate it along the length. So, then you will get that. Now, then in fact, suppose I am talking for the mode shape, the mode n, some arbitrary mode. So, therefore, when you do that, then my total force F t is nothing but integration, it is 0 to L, then it is P t Dirac delta function x naught x 0 multiplied by this mode omega n x into dx, which is tells you nothing but P t into omega n into x naught. So, this is how you can get in now what the idea is, you have this shape. Let me just draw the shape and let me explain. So, let me erase some part of it, because I want to have these things. So, just erasing this part and showing you. Now, idea, what the idea is as follows. What I am thinking that this is along the length, okay, and then you are having some sections, and each sections you are calculating the green water or any green water or slamming pressure P t, okay, and then you multiply this with the x minus some it is let us say x I. Okay. So, then the total force F t is basically the collection of all this force, then integrating from 0 to L and multiplying with that omega n into x into dx. So, what is happening actually, the total force you are getting, let us say you can make let us say n sections, let us say. So, it is become P t into omega n into x of all these points. So, x I can say. So, that is how actually you can approximate the slamming load. So, this is many ways you can do that, right. You take the pressure at each point and you multiply with a Dirac delta function, and then actually you can integrate along the length. So, this is how you can incorporate the slamming load. You see, that is what actually he has done. I mean, in this expression also the same thing has been done. We multiply this with this motion, right. Okay. So, now this is how we can incorporate in the flexible code also the slamming and the green water. Now, as I told you that in the last part of this very quickly we are going to show you that a 3-step method, okay. And if you have this panel method code or if you have the boundary element code, and then if you can develop this CFD based method, then actually very rigorous way you can calculate the effect of the slamming and the green water into the hydroelastic code. Now, you see okay, before that I just show you this the results. You can see here using this semi analytic method that this compared with the proper the CFD result. As I told you that this method may not be very well capture the detailed phenomena, but if you are talking about the magnitude of the force, it actually really captures very well the magnitude of the force, right. And this is the some time history for the green water load. Now, similarly for the slamming load also, this is how actually the pressure varies. If you see some paper or some published paper, you can see that the slamming load normally varies along the wedge in this fashion, is from 0 it goes max and suddenly dropped, and that is how actually we can get the that pressure history of the slamming load also. So, you can see that at least you can now you can see that there is some effect also, some visible effect also one can see. Now, it is actually on the that some RAOs of the sagging moment. So, you can see that it has some kind of effect, right. Okay. So, now later this present hydroelectric analysis is just attempt to study that how we can incorporate the hydrodynamic load into the into this hydroelastic solver, right. Okay. So, let us move into the next problem. Now, here let me discuss very quickly, I will discuss about the 3-step coupled BEM-FEM-CFD based method. Now, this is the flow chart. Now, here I just go quickly that we have this input parameter over here, and then we initialize all this data, right. And then actually from here we can go in 3 different solver. We first move to the structural solver, we go to the boundary element solver, and again we go to the CFD solver. Now, from this boundary element solver, I calculate all these global forces, which is radiation, diffraction, fruit curl off, and we pass into the generalized force matrix. From here also we can calculate from CFD the green water and or I mean that green water load, and then we can find in the store in the global matrix. Now, then we solving the equation of motion, we get the displacement, velocity, acceleration, and again we can back to the BEM solver, but here it is a 3-step method. So, this whole exercise actually we are assuming the body is rigid and we are calculating the green water load. So, here we are not coupled it, that is why I call the 3-step method. That means, initially you give some rigid body motion to the solver and you calculate separately the slamming load, and then that slamming load you incorporate into the finite element solver. Okay. Why it is justified? Because we assume that that elastic mode does not affect the slamming load as such. It is only the rigid mode which affects the slamming load. So, that is why we did not consider the flexible mode, only consider the rigid mode and we calculate the slamming load. Then, however, this slamming load influence the structural deflection. So, that is why we are using this 3-step method. Okay. Now, here you can see that the total force here, it is the due to radiation, due to fluid curve and due to hydrostatic and due to green water, right. Now, here the radiation and fluid curve is directly coming from our BEM solver, right. So, now you know that this is the pressure and we know how to get this pressure from the hydrodynamic course, we discussed a lot. So, this is how we are getting it. Now, the restoring force also very important, right. In case of hydroelasticity, it is not as same as the rigid body. So, here actually we can calculate the hydrostatic force is the difference between the instantaneous hydrostatic force minus the initial hydrostatic force, right. So, this is how actually normally we calculate the hydrostatic force at that particular time. Now, the green water load we use the, now we can use the Navier-Stokes equation together with the volume of fraction VOF method. Now, here that is what my point, like, and that is the whole point of discussing this here, because this is the out of the scope of this particular course, but we have to be very well aware of the fact that if you want to calculate this green water and slamming load with proper detail, one has to calculate this using the Navier-Stokes equation solver or classical CFD solver. Okay. So, this is the basic equation that you are going to use to get the green water load using the CFD. Now, I am not going to discuss in detail what is this, but maybe as a researcher, if you want to do, if you have this the standard software, you can incorporate the green water load using this Navier-Stokes equation as well as the volume of fluid method. Okay. And now, this is the reference that you can use to find out that how you can get the slamming load into the solver. Okay. So, now in this class we discuss how you can incorporate the non-linear slamming load, and also in the previous class we discussed how you can incorporate the green water load into your boundary element solver. Okay. So, this is the advantage of the time domain boundary element solver. In frequency domain solver you cannot do this, right. So, therefore, it is better to have a time domain code, because such nonlinear force actually you can include into the solver. And I think by this time, by that time you have the boundary element code based on impulse response function, right. So, try to write this dam break model and this Wagner model and get a more realistic solver for you. Okay. Thank you very much.